The topic of this video is electric fields. By the time you finish watching this video, you should be able to do the following things. Define electric field strength in both words and as an equation. Use the definition of field strength in Coulomb's law to derive an equation to find the electric field strength at a point. Understand the meaning of electric field lines, and be able to draw electric field lines for parallel charge plates and single or multiple charge systems. Lastly, you should be able to apply the electric field strength equation to a single charge. So let's get started by explaining what exactly electric field strength is. So in the past we've talked about gravitational fields, and fields in physics are cases in which two separate objects exert forces on one another without actually touching. And so an electric field is an area of space over which a force exerts a charge. And this force is going to be related to Coulomb's law that we discussed earlier. So for example, if I take a 2 nanocoulomb charge, here we are, and I look at some point, call this point P, which is 10 micrometers away from my 2 nanocoulomb charge, we'll say it's in a vacuum, this would be within the electric field of this 2 nanocoulomb charge. So any other charge that I put at point P will experience a force according to Coulomb's law from the 2 nanocoulomb charge. So if, for example, I place at point P, I'm going to just draw the same situation below here. I place a 1 nanocoulomb charge. That 1 nanocoulomb charge would feel a force from the 2 nanocoulomb charge of 178 newtons according to Coulomb's law. If I were to, at that same point, I'll draw it again below, place a 2 nanocoulomb charge, that charge would feel a 356 newton force from the 2 nanocoulomb charge. So we see that at point P, two different charges feel a different amount of force. And so in order to describe the strength of the 2 nanocoulomb's electric field at this point, we come up with a different quantity called electric field strength. And what electric field strength does is it's the force per unit charge experienced by a small positive point charge at that point, in this case point P. So if we were to divide the force experienced by the charge at point P, we would get the electric field strength. And we can describe the electric field strength using this equation here. E, electric field strength, is equal to force divided by charge. So we see if we divide the charge of, and so by using this equation, we take the force exerted by the charge at that point, divided by the charge it's being exerted on, the 1 nanocoulomb, we see, or the 2 nanocoulomb in this case, we see that the electric field strength is about 179 times 10 to the 9 newtons for every coulomb for both cases. So the electric field strength at point P is 178, times 10 to the 9 for both cases. So now that we can calculate the electric field strength based on knowing the amount of force an object at that point P is experiencing, we can derive a separate equation if we just want to know what the electric field strength at that point is, just based on knowing the charge that's generating that electric. So let's make ourselves some room. So we can find this equation by combining Coulomb's law with our definition of an electric field strength. So if we plug in Coulomb's law, force here, plug it into this equation here, we get, and our q's cancel out, our small q's, and we're just left with the equation, electric field strength is equal to the constant times the charge that's generating the electric field divided by the distance to the point you're interested squared. So now that we know how to calculate the magnitude of our electric field, how can we find the directions of our electric fields? And something to help you figure that out are called field lines. So field lines represent basically lines of force. And remember that we defined our electric field by the force on a small positive point charge. Remember, we said positive point charge. So you can think of electric field lines as the path a positive charge would take if placed at that point in the electric field and it was free to move around. And there's some rules for drawing these field lines. There's 4 rules. The first rule is that they point positive to negative. So this means if I had a positive point charge here or a negative point charge here, and I were to draw my field lines, they would point out from a positive charge and into a negative charge. And this makes sense given the fact that we define the electric field strength based on a positive point charge. So if I were to put a positive charge at point P here, it would be pushed away from my positive point charge. Or if I put a positive point charge here, it would be pulled into my negative point charge. So it just makes sense that they would follow these arrows because we're basing this on a positive charge. The second rule is that the lines are evenly spaced. So you can see above here how I've drawn the lines so that they're roughly separated by an equal amount. They're not all bunched on one side or the other. The third rule is a greater number of lines indicate a region where the electric field is stronger. So for example, if I had a 1 Coulomb charge or a 2 Coulomb charge, the 1 Coulomb charge would have a few lines, whereas the 2 Coulomb charge, in the same amount of area, we would expect to have twice as many lines. So it would have a greater amount of field. So if I were to look at this region for both, I would see that the 2 Coulomb charge has twice as many lines as the 1 Coulomb charge. The fourth rule is that the lines meet the surface of a conductor at 90 degrees. So if we were to visualize this, so if I have a spherical conductor and I have maybe it's a positively charged spherical conductor, the electric field lines, if we were to zoom in, we would see that they all meet the surface of the conductor at 90 degrees. So let's apply these rules to something more complex situations involving parallel plates and multiple charges. So for our first example, let's do a positive point charge and a negative point charge. So according to our first rule for electric field lines, our field lines are going to point positive to negative. So if I were to have a field line that was coming out of the bottom of my positive charge, it would bend to meet the negative field charge. The same for the top. And so my electric field lines bend from positive to negative, and they all point positive to negative. And so I'll just add a few more lines, making sure all of my arrows point positive to negative. If we were to have a similar situation, only maybe now we have 2 like charges, so I'll just do 2 positive charges, but 2 negative charges would be the same situation. I won't have charges pointing toward a negative charge, so what we would see is the charges would point away from my positive charge, but it's important to remember field lines do not ever cross, so because they have to stay evenly spaced. So in this case, the electric field lines coming out from my positive charges are going to come toward each other and form an asymptote where they'll approach each other but they'll never meet. And we'll have a similar situation for the bottom, and because that electric field line bent, all the other electric field lines have to bend too. So it's ugly, but that's how it is. Make sure your arrows point in the right direction away from the positive charge. The last situation we'll do is for 2 parallel plates. So we'll have a metal plate on top that has a positive charge, and we'll have a plate on the bottom that has a negative charge. Now, just like any other situation, my field lines will point positive to negative from the positive plate to the negative plate. And because there's some the field lines aren't going to be perfectly straight on the edge here. You're going to have curved lines coming out around the edge, which are called edge effects. You're going to see this situation a lot with two parallel plates. That people like to use these for physics questions because you need to remember this. The electric field strength is constant between two parallel plates. Okay, and that's it for field lines. Let's put what we learned to use with an example. So our example asks us, what is the electric field strength 30 centimeters from a 15 microcoulomb point charge? So we'll start off by drawing a picture so we can kind of picture what we're dealing with. So we have a 15 microcoulomb point charge, and then I'm interested in a point P that is 30 centimeters away from this point charge. So I don't know what the charge is at point P because we're just dealing with a point in a field. We're not dealing with another charge. So I'm going to use the equation we derived earlier to solve this question. So electric field strength is equal to K, Coulomb's constant, times the charge that's generating the electric field, divided by the distance to the point we're interested in, squared. So Coulomb's constant is 8.9 times 10 to the 9. The charge we're interested in is 15 microcoulombs, and it is 30 centimeters away. Don't forget to square it. A lot of students miss the squaring and get the questions wrong. So we see that the electric field strength at this point is 1.5 times 10 to the 6th newtons per coulomb. And because electric field strength is a vector, we need to give it a direction also. So I'm going to say, because remember we define it as a positive point charge, so if I were to place a point charge at point P, right here, if I were to put a positive charge here, it would be repelled by the other positive charge. So I'm going to say that it's pushed to the right. Okay? So what can we do with this information? So what if we would put a 1 microcoulomb charge at point P? So in the previous question, what if we took our 15 microcoulomb point charge, which is 30 centimeters away, and we would put our 1 microcoulomb charge at that point. So we could solve this question as we did before using Coulomb's law, but in the previous question we found that the electric field strength at point P was 1.5 times 10 to the 6th newtons per coulomb. So we know that for every coulomb of charge at that point, it's going to feel 1.5 times 10 to the 6th newtons of charge. So we can use the definition of electric field strength. Electric field strength is equal to force over charge. Rearrange this equation to find the force, and then all we have to do is some simple substitution. So the electric field strength at point P was 1.5 times 10 to the 6th newtons per coulomb. The charge we've placed at point P was 1 microcoulomb. So we see that the force would be 1.5 newtons. And because this is a positive point charge, it's going to feel a force in the direction of the electric field, which is to the right. Okay, that's it for now.